Hey, Sahan.
Hi, can you hear me?
Yes, we can. I'm afraid I can't see you though your video is off at the moment.
Okay, let me.
Yeah.
Yes, let me turn my video on. It still says that the host has stopped sharing my video.
Okay. Let's see about that.
So I shared the screen.
Okay.
Can you see my screen?
Yeah, we can.
Okay, great.
Perfect. Cool. So thanks for joining us, Sahan, for the next session, which is our first session actually in the data track, which is big data for large-scale machine learning with Apache Spark. So the amount of actionable data that is actually available to organizations has exploded in the last 2 decades. This has led to the opportunity for businesses to harness that data and create value. In this talk, our speaker Sahan Bulathwela describes how Apache Spark, a big data technology that has a Python programming interface, can be utilized to create big data products. As always, to the audience, do feel free to ask any questions that you may have in the Q&A box below, which is at the bottom of your screen. And if we have some time at the end of the session, we will take them up. So without further ado, please join me in welcoming Sahan, who is a researcher at the University College of London, whose research lies predominantly in the area of leveraging artificial intelligence for lifelong education. Welcome to PyCon, Sahan.
Hi, thank you very much. And yes, hello, good morning, everyone. Welcome to today's session. I'm Sahan, and I'm still unable to share my video feed. Is that okay if I carry on like this?
Yeah, go for it. In the meantime, in the background, we will see what we can do. Could you give it a shot now?
Okay, I think,
Perfect.
yes, I think it's working now, isn't it?
All righty.
Okay, let me, yes, okay. Hi, everyone. Good morning, and welcome to today's conference. And we are going to focus on big data for large-scale machine learning with Apache Spark, which is an open source software that is available for us to use. And just a brief introduction. I think the organizers gave a great introduction about myself, and I would like to thank them for taking all the hard work in organizing this conference as well. At a very timely, time. I'm Sahan. I'm currently affiliated with University College London in the Center for Artificial Intelligence. My research is mainly about how to leverage artificial intelligence in education and sustainable development, specifically in the areas of educational recommendation and knowledge management. I have a few collaborations with EU projects, and also I work in how to leverage AI in disability innovation, like in building assistive products and making sense of that information. If you want more information about my current work, and also if you want to get in contact with me, I have also put my personal website that you can go explore and also reach out to me. So today what we are going to do is we have a few things I want to cover. To start with, to define big data, and then figure out how we can tackle big data with scaling out infrastructure. And then we are going to focus the majority of the talk on Apache Spark, which is a distributed computing framework that is available to us. I'm going to spend some time explaining the core ideas behind Apache Spark and how the programming paradigm changes from conventional type of programming that we'll do in a Python software. And then go into the extensions of Apache Spark, like the DataFrame API. Some of you who are in data already might know about Pandas DataFrames. So the big data equivalent of that in Apache Spark is the DataFrame API. And then how we can use these data frames to do large-scale machine learning in the cases where your data does not fit in a conventional computing system. And finally, we will have some time for questions and answers. Yes, so what is big data? I'm not going to spend a lot of time on these things, but it's good to get everyone on the same page. So Wikipedia, one of the most referred knowledge bases in the world, refers to big data as a field where you try to analyze, systematically extract information from, or in general deal with data sets that are too large or complex to be dealt with in a traditional data processing system. So in a layman's, what this means is if the data set that we are dealing with is very hard to deal with in a conventional computing system, for example, like a laptop or like a personal computer that we have, we can think of this data as big data. And why has big data become a thing in the last few years? As you can see from this plot, which is only, tracking the information overload until 2007, which, was more than a decade from now, before. You can see that since 2000s, the amount of digital data that is being created has exploded in the world. And in 2007, there were about 280 exabytes. Exabytes are like, even bigger than petabytes of data out there. And with that, conventionally, what would the businesses want to do? They want to extract information and value from this. So this is why, big data has become a thing. And now let's look at how we can deal with big data. So one of the conventional, natural things you would want to do is if your data set that you're working with does not fit in the common paradigm of a laptop computer or a PC computer, you would go to a specialized vendor like Dell or Oracle, and they would have these supercomputing systems that are, much larger in size, that would have a lot of RAM, a lot of CPU. You would try to, purchase one of those because, ideally your new bigger data set would fit in one of these, high performance computing systems. So this approach is called scaling up because you have the same computer and you're vertically increasing the specification of your hardware system. However, there is an alternative to this, which has been coming up in the last few, since like early 2000s, which is instead of, scaling up into buying a bigger box, what you do is you take additional boxes. You have a computer with you, you buy 2 other computers and you connect them through the network and you put a software layer on top of that so that the end user sees this compute system as a unified system. So through the software layer, it looks like a massive computer with a lot of RAM and CPU, but under the hood, it's a bunch of computers connected together. By doing this, what you can do is you can take this large data set and then distribute chunks of this data set into different computers. And you can store it in the RAM of these different computers, and also you can process them. So this approach is called scaling out, and this has become one of the more popular paradigms of scaling infrastructure in the web scale era, where we deal with petabytes and terabytes of data. And this is because there are some interesting benefits to this. One thing is you can scale your system linearly, which means when you want to scale your system, all you need to do is keep adding new boxes, and the only cost you are taking is the network complexity. Whereas you can also use domestic hardware like computers that you can buy readily through Amazon or any other software hardware vendor. You don't have to go to a specialized vendor and spend exponentially large amount of money to get a bigger box, which is cheaper, and also which is cheaper in terms of not having to invest on an entirely new hardware system. And then it's also elastic in terms of scaling, in the sense like, for example, over time, the next, upgrade that you want to do is to increase 100 gigabytes of RAM in your compute system. Let's say that's the scenario. Your vendor might say, no, the next upgrade we have is 300 gigabytes. You either take it or you don't. Whereas in this type of system, all you need to do is add new infrastructure based on the need you have. And you also get this added, advantage of the system not failing entirely, because, only 1 or 2 of these nodes can go down at any given time, and the software is built in a way that it will handle these type of issues. Obviously, there are limitations, and it's relatively complex to maintain. You need more hardware expertise and software expertise to do this. Today, we are going to work on, when we are working with the system like this, the code is, the data is fragmented in different parts of a compute system. We also have to think about writing our code in a different way, because, for example, you can't just have a conventional for loop that will run on a data set in your RAM, because now the data is in different places. So you need to change your paradigm of writing code, which will be the main focus of today's talk. So to do this, one of the open source frameworks that is available and that has matured with a large population of data practitioners in the past is Apache Spark. Apache Spark is not a machine learning system. It's a generic data processing engine. So what it can do is it can ingest data from different data sources like, SQL databases, BigQuery type of big data, NoSQL databases, from block storage like S3, and then it runs a series of transformations on the data to do the manipulations we want to do in these large data sets. And then it also output data into different data sources. And primarily, the Spark system uses MapReduce paradigm, which is something that we are going to look at going forward today. If you look at the Spark ecosystem, it's it has a core component on top of which there are subcomponents that are specifically catering different types of applications. For example, if your data is in motion, which means if you're constantly getting fed with large data, you have Spark streaming for that. When you want to make sense of data, when you want to add value to your data, there's the MLlib machine learning library, the GraphX library that can help you work with network or graph. And if you have schematic nature in your data where you have further information than just unstructured text or unstructured data structures, then you can use columns, you can use rows, do filtering on top of that. To do that, you have Spark SQL and DataFrame API. And why is Apache Spark relevant to this community? That is mainly because Apache Spark also has a Python interface that you can use to instruct Apache Spark on how to work with a large-scale data set. As a programmer, you can use Python to, make use of this framework. And this subsystem is called PySpark because it is to do with Python. And we are going to start with, in the Apache Spark, there is a core API, which is the heart of the software. And then everything is built on top of that. And what does the core API do? The core API has all the algorithms to deal with when you get a large data set fed into this hardware system that has multiple computers. How do I distribute the data? And then when I get instructions to run on different lines of this big data set, how do I distribute these functions across the cluster? And how do I get feedback? All of that is written in the core API. And then based on the application, there are extensions that are available in the subcomponents like streaming, MLlib, etc. So when we are working with Apache Spark or large data sets with Apache Spark, the main data structure that we want to familiarize with is the RDD data structure. So RDD it stands for Resilient Distributed Data Set. So what is RDD? An RDD is the data structure that takes your large data set that doesn't fit in your laptop, for example, and store it across this cluster of computers. As a Python veteran, you can imagine this as the distributed version of a Python list. You have the same type of a collection of bits, but it's not in a single RAM in a computer. It's spread across multiple computers now. And the RDD, the Spark core, has all the algorithms to figure out, okay, there are these parts of this, structure in these different machines, and how to deal with these physical realization of these information. And here we also have a visualization of how this looks like. So imagine we have a collection of data that we read from a file. Imagine this is a large file that has 1 billion, different values. So what Apache Spark does is, in this scenario, we have 4 computers that are in the Spark cluster. When we load this data set, Apache Spark will decide, okay, I'm going to spread these values in different computers, because one thing I can, manage all of them in the RAM of these computers. Then if I want to do some computation, we can also, use parallelism to work on these different parts of the data. That's the core idea behind an RDD. And once you have spread the data like this in a, in a compute cluster, we also have the challenge now, in Python, if we want to, iterate over this entire data set and write, do a transformation on the data, we would have to use something like a for loop. But now you cannot use a for loop because all the data doesn't house in a single RAM in a single computer. So as I mentioned earlier, we have to change the paradigm using which we are handling or instructing the Spark system to how to deal with this data. So to do this, we use what is called the MapReduce paradigm, where rather than saying like, in a procedural way, how to do things sequentially, we we code in a way that things can be run parallelly. So one thing that we need to, keep in mind is when we want to run MapReduce code, we need the data has to meet a certain condition, which is that the data has to be embarrassingly parallelizable. So what does that mean? That means that the data cannot have any dependencies. Everything has to be able to run massively parallelly. In the sense, you can run a function on one data point in this data set, and it should not affect running the same function in the other parts of the data set. So if you have data like this, you can use the MapReduce paradigm. And there are, Apache Spark gives you a whole lot of, functions that you can do in order to do transformations in these distributed RDDs. But what we are going to look at right now is I'm going to point out in this talk, in the interest of time, some of the core functionalities that will allow you to generalize this knowledge into other, RDD transformations that you can do with Apache Spark. One of the core functions that, Apache Spark provides is the map function. And you can see this is, Python examples of how a map function is written. So you have this resilient distributed data set, which is the data that we have loaded from a big data set. And we say we want to use the map function. The map function is also available in Python. So some of you might already be familiar with what a map function does. You can define a function using, which you can run on every element of a list. So the idea here is the same, but instead of running it in a list, it runs it on this resilient distributed data set that is distributed across the entire cluster. So here we have this transformation that we want to run. So what it does is it takes every element in the RDD and then it runs this transformation. So you end up with a new RDD, which is RDD2, which is the square of the previous RDD. So similarly, you also have another function called filter. So filter function, as you can see, can be used to eliminate certain rows from your RDD. So if you want to do filtering of the elements, you can do that parallelly using the filter function. And here we have a function that can take an input and provides an output. Here, what we have is a function that can evaluate into a Boolean value. So if the value evaluates to true, that number will remain in the resultant RDD. Otherwise, that number will get discarded from the resultant RDD. So these are like some of like two of the core functionalities you can use, but there are a heap of other API functions that are available in Apache Spark, which you can find in the documentation that I will heavily encourage you to work with. And these two functions that we looked at so far, they work with, in element wise. So you have this embarrassingly parallelism where you take on one value and you transform it to another value. Here you take one value, you transform it to another value, or you drop it. However, sometimes you would want to take these values and aggregate them together. This is one of the core functionalities you will need in a software system. Because even in a for loop, we might calculate a sum, we might calculate a mean. So to do these type of things, MapReduce also provides us a reduce function. So the reduce function allows us to interact with multiple items in this RDD rather than working with single items separately. And what we do here is, the reduce function, for example, can be used to aggregate things together. And here we have an example of how the reduce function is used, where in the RDD, we invoke the reduce function and we define the instruction in a way that it takes two parameters and produces one parameter, one output. So here you can see we have three values, but if you take pairs, any two independent pairs of these values, you can run this function on it. So, for example, A can be 2 and B can be 3, or A can be 3 and B can be 3 as well. And we'll end up with, so if you take this, what will happen is 2 and 3 will get added together, which is 5. Then that element can be added to this value. Or if there were 4 values, these two things can, add together. And then the intermediary values can add together. So the whole point is with log number of, complexity, you will be able to reduce or aggregate the entire data set into a smaller set of numbers. So this is, the reduce paradigm. And if you read the MapReduce paper that was, released by Google Research, which, sort of gave birth to the whole Hadoop era of things, they explain that, most of the web scale operations that you do in a company like Google, Facebook, or advertising startup, etc., many of these transformations can be, it can be written using this map and reduce operations. And that is why this technology also has picked up a lot in the ecosystem. So these are like, some of the, this is a flavor of how you can take your Python code and transform it into this massively parallelizable form that you can use with the scaled out infrastructure paradigm. And here, just to reinforce your understanding, I have a small Apache Spark example here. So as I said earlier, Apache Spark reads from data sources, and there are separate functions that we can use to tell Apache Spark where to read from. And based on that, Apache Spark already knows how to use what protocol, how to contact that data source. If we give the URL, or if it's a database, the database connections string, based on that, it can read the data. So here we are reading a text file that has these JSON objects. So when you read the text file, they are all strings. And then the first thing we do is we take the JSON loads function, which is a standard Python function, and we are running it on every element of this data set. And here you can see Apache Spark has already distributed this data into, let's assume in this scenario we have a cluster of 3 different machines. For the sake of simplicity, I mean, Spark also can have multiple chunks of this data residing in the same machine to take use of the multi-core parallelism. But for simplicity, let's assume there are 3 computers that have single cores, and we have these we take this data and we chunk it into 3 different parts. and we can run this function on each line parallelly. So we end up with a Python dictionary. And then what we are doing, so we do the JSON loading, and then we are running a filter after that, where if the flag is 1, it will get remained, otherwise it will get dropped. So we have this Boolean flag, which we have done as well. And you can see that all of these lines can be evaluated parallelly. This is the whole, power of this paradigm. And going from there, what we are doing is we are, transforming this dictionary into a tuple using Python as well. And so this is the green bit now, which is in this visualization. And then we are going into a reduce. And to reduce, I'm using specifically a function called reduce by key here, where Spark will already know that the first item in the tuple is the key and the second item is the value. And here what I'm saying is for every key, I want to run this reduction. So because Apache Spark has these underlying algorithms based on these values, it can then, in this phase, send every item in the data set that is scattered around different machines in the cluster. It can send it to a same physical machine so that you can aggregate everything together without, missing anything. So here you can see everything to do with A has come here, everything to do with B has also come here, and everything to do with C has gone here. And then what you can do is you can use this lambda function. So you take these two values, you add them together. If there were 3 values, you'll add 2 values together and then take that value and add it with the other value. So we can keep doing that, and we end up with the aggregate. And once we aggregate it, we can also have the option to then, call it into a single machine so that we can use it in our Python software, for example. Most of the use cases that we use, we end up with something like this, where you have, you start with a terabyte scale data set, but eventually what you want is a meaningful summary or a meaningful transformation of that information that is much less, in terms of the volume. So for example, what we used to do in my previous work, I used to work with advertising data, where we would get about 1.6 terabytes of user behavior data in our systems every day. And one of the pipelines that we designed, what it's meant to do is take these individual events, which are billions of events, and then group them, reduce them based on the cookie ID, so that we gather all the data from the same person to one place. We run a bunch of transformations, and then we have a reduced data set, which is a few gigabytes, that gives us some summary statistics of these users, which becomes features into our machine learning pipelines. So doing something like this, we would start with like a very big cluster where we can process all of this data in a matter of 30 minutes, these terabytes of data, and we end up with a several gigabyte data set that we can push into a big machine in Amazon, and then even something like scikit-learn, which is not a large scale machine learning library. So these are type of use cases that you usually use with MapReduce. And the specific part where we have to move data across the network in this compute cluster is also called shuffling the data. But the main thing that you have to sort of understand here is that this whole pipeline is a variation of maps and reducers, where maps is you take the values independently and you transform it into a new value. Then reducing is about aggregating the values in this collection together. So that's kind of like a an introduction flavor to how MapReduce paradigm works and how it works in the context of PySpark, which is a Python interface to this MapReduce compute engine, which could be beneficial for you to use as well. And so far the thing is, we are dealing with data as this unstructured or semi-structured representations where, for example, if it's a JSON file, all of these lines can have a very different structure. This can have a certain set of keys. This next line can have a completely different set of keys. So when we are dealing with, complex data like that, the RDD or the core API, where we have to define exactly how to deal with the data, is useful to us. But in many cases, in many business cases, the businesses have already put in the infrastructure to take this type of semi-structured or unstructured data and transform it into a more structured type of data. For example, we might have large SQL tables that has specific columns, and these columns have data types associated with it. And, there's a lot more meaningful information that we can use in our data processing. So usually if you're working with a small enough data set, you would use something like pandas to deal with this type of tabular data. And Apache Spark has a counterpart that can help you work with structured big data that still won't fit in your laptop. And that's called either Spark. You can use Spark SQL or the DataFrames API, which is an extension of the core API that we just looked at in order to familiarize with MapReduce. And what is a Spark data frame? A Spark data frame is again a collection of objects. However, they are not just independent objects. They have this notion of named columns, which means there is a schema involved, which you can see here. So here the main constraint is, although you have terabytes of data, they have a structure that we can exploit. And this is very similar to pandas and R data frames, if you have been working with pandas data frames, for example. But the main notion is that you can think of it as these tables that have additional constraints associated with the fields. And apart from, RDDs, where you can, load literally anything like a text file or a, XML file by reading it as text and using our Pythonic functions to make it more meaningful. If you already have a structured data set, the DataFrames API provides us other, ingestion technologies or techniques that we can directly load data from these data structures that have schema already. So for example, CSVs have a tabular format. JSON, although can be semi-structured, you can have JSON lists where all the dictionaries or all the JSON objects are adhering to the same structure. JDBC is to do with databases. Databases inherently has a schema associated with it. Then we have the NoSQL counterparts of JDBC, which are large relational databases. You can have things like BigQuery, or Amazon has Redshift. These type of databases still has schema associated with it. And these things can be directly loaded into Spark data frames, and it will treat these data frames as rows that have these columns associated with it. And with data frames as well, you have similar transformations that you can do, just like that what we familiarized earlier, where you have the select function that you can use to take a row and select columns out of that. So this is going hand in hand with SQL. And then we also have things like group by, and when you have two data frames, you can use the join functions to connect them together based on several columns. And what you need to know is, what we looked at earlier is data frame sits on top of Spark API, which means when you do these things like using the where clause or use a join, what Spark does is it takes this data frame and then uses the MapReduce logic that is already in the Spark core API to do these type of transformations. So to the end user, you see like, oh, I have two tables, and then Spark is connecting them together. But what Spark is doing under the hood is it takes these data frames, which is, at the end of the day, RDDs that also have these additional constraints. Then it can use the same, map, reduce, filter type of functions to do the same functionalities, like using the filter, using the where clause, using the select clause in order to do the transformation. So, I mean, that is how I'm going to give you an introduction of how it extends to data frames and RDDs. And for you to, go in your spare time and get more familiarity in this field, or in, expand your knowledge on what I spoke about earlier, I have put two videos here, which is, a tutorial I ran with one of my previous colleagues at the London Spark meetup, which gives you a much more detailed explanation of all of these different functions. And it's also incorporated with Python notebooks that you can use to look at the code. You can try your own code, etc. And for you to understand how flexible and applicable MapReduce paradigm is, I would also highly recommend you to refer to chapter 2 of Mining Massive Data Sets book, where that chapter is all about taking different SQL operations and explaining how these operations actually happen in MapReduce paradigm. That gives you a very good understanding of how powerful and how to generalize the notion of MapReduce to literally majority of the transformations we have to do in our day-to-day life and work. So with that, I'm going to go into, okay, we looked at Apache Spark RDDs, and then we went to DataFrames. That now we have a pandas DataFrame-like table in our, compute system. In a conventional machine learning pipeline, what would we do? We start with a data set. We use pandas to transform that into a data frame. And then, we can feed that into something like scikit-learn, where we feed the table, we can train, fit the model, then we can predict from another pandas data frame. So that's like the conventional machine learning pipeline if we were to work in our personal computer. Now we have a big file that does not fit in our computer. So what do? Here, it's also, we have the same counterparts where, we have the big CSV file now, and that we have this compute cluster that can have multiple machines, where in aggregation, the RAM can hold this data set. We can use Apache Spark DataFrame API to load this, big data set into these multiple machines. And then what we can do is we can feed this Spark data frame into one of the large-scale machine learning libraries or functions in the Spark machine learning library. And how does this workflow look like? So we have this big CSV file. So what we would do is we would either use the core Spark RDD API or the DataFrame API to take the raw data and do the transformations we need in order to create the data that we want to feed into the machine learning pipeline. So that we can call the ETL part of the pipeline, where we extract, transform, and load the data. And then we transform into a table that has meaningful schema, which is the PySpark data frame. And then what we can do is we can use the MLlib library. We take this data frame, and there are a series of functions. You can see here, I have taken an extract from the documentation of the MLlib library, where you have various different, model families that deal with different types of machine learning tasks. It also has certain utilities that you can use to transform features. For example, if you have text data, there are feature pipelines that will take that text data and convert them into term frequency, inverse document frequency vectors. So all of these things you can run through on your data frame. And then based on that, you can load this data into the cluster and use a parallel machine learning version of linear regression, logistic regression, decision tree, random forest, etc., to train a model at scale with using this entire data set. And once we have that model, we can then use Spark again to feed a lot of data in large scale parallelly into the cluster and get predictions on this data. So here you can see how the framework can shift between the core RDD and then data frame paradigms over time in this transaction, in this pipeline. And all of this happens in a cluster of computers rather than in a single computer. And the code for something like this in PySpark looks a bit like this, where, as you can see here, we are loading the data, and there are, machine learning specific formats that Spark understands. So otherwise you can just load from a text file or a JSON file and do a bunch of maps, filters, etc. to make the data the way you want. And then you end up with a data frame, a Spark data frame. And in Apache Spark itself, there are families of algorithms that you can instantiate, which is very similar to the scikit-learn API in terms of how you define the programming. And then we have a single API where you have a fit function. Instead of passing a NumPy array or a pandas data frame, you are passing this PySpark data frame as an input, and it will train a model with parameters associated with this model that are conditioned on this training data. And once we do that, we have a model that we can be familiar with. It can be a linear model like logistic regression. It could be a random forest model that can have these different trees and parameters associated with it. And then we also have, so here we have, different parameters that you can fit into the logistic regression. And then finally, you have a transform function as well, which is not here in this code example, which allows you to then pass a new data frame with the features that we use for the logistic regression training and get predictions at scale as well. So all of this happens in a cluster that has multiple computers, which means you can use terabytes or peta-bytes data to train your models because your infrastructure can handle that. And then you can do the same in the prediction time. So when we are working with machine learning pipelines, especially in the context of big data, we need to think about a few considerations. The first thing is, even if the data is small, when you are doing transformations in your data, you can still use them, use PySpark because, installing PySpark is very simple. You just do pip install PySpark. And it automatically knows that, it can detect how many cores are in your computer and then, use parallelism to work with, we write massively parallelizable code. So Spark knows how to take that code and run it in your multi-core system anyway. So even if you have a data set that is considerably small, you can still leverage parallelism very simply by writing your code in Spark style. And this is something that I use very often because even, personally, I have a computer that has 12 cores in it. So even if my data set is, 4,000 values, I can write it, write the code in a way that it can parallelize that. And the nice thing is, if I then get handed over a new data set with the same format, which has, 400 billion columns, I can take that code, put it in a cluster and run it without doing any changes to the code. So that's an advantage, especially in the context of data processing that you benefit by, using Spark. However, when you are training machine learning algorithms, you need to understand that in machine learning, there's this concept called no free lunch theorem, where when you are gaining something, you're usually sacrificing something else. So when you work with these large-scale parallel machine learning algorithms, you don't see, the algorithm doesn't see all of the data when it tunes the parameters. So what it usually does is it trains the parameters based on the subset of data in the different computers, and from time to time they share parameters to sort of come to a consensus. So this can be not as effective and accurate as training in a single core, or training with all of the data in the RAM where there is full visibility. So if your training data can fit in your RAM, using a distributed machine learning approach might be a bit of an overkill, and it can also compromise a tiny bit of accuracy and precision from your machine learning task. So that is not to be confused with data processing. So this is to do with specifically fitting models. So in that case, usually, using something like scikit-learn is much more effective. And given it is machine learning or not, you should test your code. Even your machine learning code, you can write tests. For example, you can have a few, training examples as your test data, and you would know if you use scikit-learn, what are the parameters you will end up with. You could see if your, machine learning logic that you have written achieves the same result. So this way you can still come up with ways to objectively test your code, which is essential, especially if you're writing very complex machine learning pipelines, to make sure that you don't have to worry about the inaccuracy of certain parts of your code. And once you have deployed a machine learning model, it is essential that you monitor how these models behave. There are two main concepts called the data shift and the concept shift that you might want to familiarize yourselves with. So one is when your data changes over time. For example, during COVID, people's shopping behavior changed over time, and that is called concept drift. People, the actual data generation process changes over time. And then you might have data shift, which is, for example, you have this data coming from, cookie data coming from your web sensors, and all of a sudden Apple decides to, block third-party cookies by default. So people's behavior hasn't changed, but the data that you see changes over. That can also heavily affect machine learning models. So monitoring these things is quite useful. In last year's PyCon, I actually did a talk about this, monitoring and operationalizing data science pipelines. So I would also, refer you to check that out. So in summary, what we looked at today is that there's a lot of data out there right now, and distributed computing with scaled out infrastructure is a great opportunity for us to tap into this. We looked at Apache Spark and the core concepts of how Apache Spark leverages parallelism today in the context of PySpark, which is the Pythonic interface to Apache Spark. And then we looked at how DataFrames can be formed from conventional RDDs. And finally, we looked at how that extends into using large-scale machine learning. So that is what I had planned for today. Thank you very much for your attention, and I hope this was a fruitful session for you. And if you need more information about my work, for example, I have the website here. And if you want to get in contact with me, you are more than welcome to do so. And I reckon we can take questions now.
Yeah. Thank you, Sahan, for that session. We do, in fact, have a couple of questions that have been logged into our chat box. So they're both from Rajita. The first one is it difficult to identify the outliers, making unstructured data sets into structured data sets? If we need to identify the outliers, what is better, before the process or after the process?
So, I mean, if we look at machine learning as a concept, the idea is that we identify outliers before we train the models, because many models that are out there are very sensitive to outliers. The loss functions can really deviate based on the, the data that it's trained on. So outlier detection usually is done before you get into, training models. And this changes, how you do this varies from profession to profession, industry to industry. But the idea is that, you have mechanisms like, for example, you can look at the distribution of the data and then look at, specific use, detect specific use cases that lie outside of that distribution. You can do that in conventional Python, where, scikit-learn, for example, has functions to do this. Similarly, you also have these counterparts in machine learning library, MLlibs. So there are a bunch of functions called statistics, and there are tests like chi-square tests, normality tests that already takes the single core version of the test and has written the MapReduce parallel version of that test. So all you do is you take your frame, you put it into this function, and it will give you the same statistics that you obtain from your in-core architecture. And after that, it's the same process regardless. Based on your profession, you have a bunch of rules. Either you learn it empirically through experimentation, or you read about your colleagues or other competitors doing similar work and learning these parameters, and then you use them to make judgments of what data you want to keep out of the process. If you think about where you do it, you would do it in the beginning, at the exploratory data analysis stage of a learning pipeline. And then you will only go to start model fitting once you have, accounted for those outliers or extreme variables. Yeah. And yes, I think we have another question from Rajita, which is about pre-trained models. So pre-trained models, I want to make a distinction here that usually, in today's world, like post-ChatGPT world, when people talk about pre-trained models, they refer to deep learning models that have been pre-trained and released. Something like Apache Spark is much more suitable for non-deep learning machine learning. If you're using, for example, the MLlib library, I would say, if you want to transform your data to feed into a deep learning model, you can still use Apache Spark, and that would be a very good way to, transform your features or data before you feed it into the deep learning model. But machine learning in the context of shallow learning or non-deep learning is where big data solutions like Apache Spark would shine, because deep learning algorithms already give you the opportunity, like CUDA is anyway parallel, and it works with data being in your hard disk, and it just uses the RAM to feed it into your GPU RAM. So you don't have this bottleneck of having to load all of the data into the RAM. So as long as you have a bunch of GPUs doing the work for you, it is massively parallelizable. So it doesn't apply as much to, Apache Spark doesn't apply as much to deep learning. But if you think about models that are logistic regressions and random forests or any other machine learning algorithm you write with MapReduce framework, once you have those parameters, the model is identical. So you have a method in you can pickle this model, and you can have a persisted representation of this model, which you can load into your machine learning pipeline later and use it for prediction. So I would say in the general context of pre-trained models, it works well, but you need to be careful on your definition of pre-trained models. If it's deep learning models, you'd rather be better off using something like TensorFlow or PyTorch to do that as well. Yes, thank you very much. You're welcome. And if you have any other questions, please fire away. Zara, you're on mute, I guess.
Sorry about that. Yeah, thank you so much, Sahan. And of course, if there are any more questions, do drop them into the Q&A box and we will take them up as soon as we can. But yeah, there we have it, our first data session of the day. Thank you, Sahan, for sharing your expertise on the architecture of Apache Spark and how it can be used to leverage distributed computing. If
Yes, thank you very much. Yeah.
If there aren't any more questions, then we will be stopping and taking a short break for lunch. Please note that we will be restarting our sessions at 1 p.m. So please be sure to be back on time so that we can move into our next round of talks. Fantastic session, Sahan. Thank you so much. I'm sure the audience enjoyed it very much as well. Thank you for being a part of PyCon 2023.
Yes, thanks everyone. Thank you organizers for making this happen. And I wish all of you have a great session ahead, and you'll get more fruitful talks coming up. And as I said, if you need any further follow-ups, please feel free to contact me. I have my email address in my website as well, and LinkedIn, anywhere. I'll be more than happy to follow up.
Thanks so much, Sahan. Thank you, guys. We'll see you soon. Please be here at 1 p.m. again.